Okay, welcome everyone. So today the topic of discussion is going to be first complexity theory part 2, and then we will get into defining trees and talking about some traversal in trees, and then time permitting I would like to introduce just two additional notions within C++ which could be beneficial later on. So we'll see how, how far we can go. So we'll get started with the complexity theory. And this is, as we introduced last week, this is about figuring out the time taken by a given algorithm. So time taken by a given algorithm. So of course, this can be time or space, but we want to reach a bound on the time. So time taken by a given algorithm, independent of the underlying architecture or compiler or OS. So how to come up with a bound on these on the time. So that will help us evaluate the quality of a given algorithm. So we introduced the big O notation, which we saw how it is acting as an upper bound. And as we mentioned, because it is acting as an upper bound, one can be very loose in terms of once coming up with an upper bound, and as a result of which we cannot just talk about how slow an algorithm is just based on the upper bound, because it could be really loose. But based on the big O, one can say that it is fast, depending on where the line is drawn in terms of the bound. So just to kind of recap, so what we wanted to say is that if you have your timing function, say Tn, right, which is what you are trying to get a bound for. So timing function for a given algorithm, suppose, goes like this. And if you have some fn, some f of n, that is going like this, and then you multiply by a constant, it will grow a little faster. And as a result of which, you can see that beyond a particular value of n, when you are multiplying with c times fn, beyond this point, this is always going to be acting as an upper bound for t of n. And that's the basic idea of order notation. Not order notation, but that's the basic idea about the big O notation being the upper bound. So this is acting as the upper bound, just to, so this is acting as the one which is going to remain always above this t of n. And the constants that you are playing with are c and this capital N. Okay, so having recapped a little bit on the bounds, let's just discuss a few practical things that we can check with respect to this big O notation. So one thing that I also discussed was the different varieties of common sort of bound that exists. The log n log n square, n cube, exponential. We discussed about those common occurrences of this f of n. So when you are coming to the logarithmic kind of notation, one obvious thing to tell is that if you have a log b base a, we know that this is going to be log b with respect to any base that you like. You can convert into, let's say, log 10 uh, by a base 10. So you can see that it will have a factor of log a of 10 with respect to log b of 10. So you can see if something is of the order, or sorry, of the, with the big O notation of the order of log b base a, then one can also say that it is with respect to log b base 10, because this is going to be constant. So it's just a constant multiplier here. So in other words, as soon as you are able to boil it down to log of any base, it is essentially equivalent to saying it is of the order of log of any other base. Okay, so some word of caution here. So let's say um, cautionary notes. So first thing is that if someone is saying n square is an element of big O of n, and they are giving a proof to you. So what is the proof that they are going to give? That choose C is equal to n, and therefore you get n square equal to C times n, which is equal to n square. And therefore we may say that n square is of the big O of n. So what is the problem in this kind of a proof?
C is not constant.
Exactly. So this is wrong. That's because C must be a constant. Okay. All right. So now let's look at one more important point. So big O notation does not always tell the whole story. So for example, if you have T of n is equal to, let's say, T1 of n is equal to n log base 2 of n, and that's your algorithm 1. Okay. And T2 of n, say another algorithm 2, it runs as 100 times n. Okay. So which algorithm would you prefer in this case? Any suggestion?
100N.
You would prefer 100n. Okay, that's kind of an obvious choice, right? Because one is linear, another is n log n. But now if you notice, so immediately somebody would conclude that algo 2 is better. The question is it? So you can see that log base to n greater than 100 only if n is greater than 2 to the power 100. So log n base 2 much less than, it's typically less than 50 in practice. Okay, so this multiplier, for it to become like a huge deal, it has to be such a big number, you can see. So therefore, in this case, you can see very clearly, because it's 100 times n, so naturally n log n would be faster in practice. So therefore, algorithm 1 is in fact better. So that's why big O notation does not tell the whole story, because if you try to express as a order notation, you will come up with this one as log of n, and this one will be order of n, and you will immediately conclude that algo 2 is better. But if you notice here that this log n, for uh, n to be really uh, it would require really n to be really large number to offset even a multiplier of 100. Any question?